Far from the bright center of a galaxy, the stars kept moving. That was the problem. The outer regions were supposed to be quieter, slower. With less material nearby, the pull holding those distant stars in place should weaken, and their motion should begin to drop. Instead, when Vera Rubin measured their speeds, the pattern refused to cooperate. Star after star, farther and farther from the center, continued moving at unexpectedly high speeds. The galaxy did not look unusual. Nothing visible appeared to be pushing those outer stars harder than expected, yet their behavior stayed the same. That created a growing mismatch between what could be seen and what was actually happening. The stars were moving as if a much stronger gravitational pull surrounded them, but the visible matter inside the galaxy did not seem capable of producing it. A prediction that should have worked was no longer matching reality. And if the measurements were correct, a disturbing possibility emerged. Either this galaxy was unlike anything expected, or the prediction itself was failing. The easiest escape was still available. Maybe the first galaxy had been misleading. Maybe something unusual about that single system had distorted the measurements and created a problem that did not exist anywhere else. So attention shifted outward. Galaxy after galaxy entered the analysis. Different shapes, different sizes, different histories, yet the same pattern kept appearing. Far from their centers, stars continued moving faster than expected. The details changed from galaxy to galaxy. The shapes were different. The visible distributions of stars were different. Yet the behavior refused to disappear. Each new measurement created the same visual contradiction. The outer regions kept acting as though a stronger gravitational pull was present than anyone could account for by looking at the galaxy itself. That changed the situation completely. A strange result inside one galaxy can be isolated. A strange result repeating across many galaxies is much harder to contain. The problem was no longer sitting in a single set of observations. It was spreading from system to system. Every additional galaxy removed another reason to dismiss the anomaly. Each new observation made it harder to argue the first result had been a mistake. The prediction about how galaxies should rotate was no longer producing reliable expectations. What should have been a local discrepancy was beginning to look like a wider failure. The observations remained stubbornly consistent. The explanation did not. Something had to preserve what was being seen, but whatever that explanation was, it had not been found yet. A way forward finally appeared. Instead of changing the laws that described motion, researchers tried changing what was inside the galaxies. The visible stars stayed where they were. The measured motions stayed the same. But now an enormous amount of additional mass was added to the calculations. Not mass that could be seen, not mass that appeared in photographs, just enough unseen mass surrounding the galaxy to strengthen its gravitational pull. And something remarkable happened. The mismatch began to disappear. The fast-moving outer stars no longer looked impossible. Their motion started matching the predictions again. On paper, the galaxies became stable. The contradiction that had spread across galaxy after galaxy suddenly looked manageable. The numbers finally started behaving again. For the first time since the contradiction appeared, there was a way to preserve what the telescopes were seeing without abandoning the underlying physics. Confidence returned. The galaxies could behave exactly as observed if most of their mass simply was not visible. The idea solved a growing problem across many systems at once. What had looked like a failure of prediction now seemed to have a workable answer. But the solution carried a consequence of its own. If most of a galaxy's mass was truly invisible, then an even larger question had quietly taken its place. Where was all of it? The idea seemed straightforward. If most of a galaxy's mass was invisible, then eventually that invisible component should reveal itself. So the search began. Years passed. The searches continued. Then decades passed. Experiments were built. Instruments became more sensitive. New detection efforts came online. Researchers kept looking for the substance that appeared to be holding galaxies together. But the result kept repeating. Nothing appeared. The instruments improved. The searches expanded. The proposed mass remained absent. That created a strange split between observation and explanation. When astronomers looked at galaxies, the motions were still there. The outer stars still moved in the same unexpected way. The measurements did not weaken. At the same time, every attempt to directly find the substance responsible continued coming up empty. The galaxies kept showing the effect. The proposed cause never appeared. And yet the mathematical solution continued working. Add the unseen mass, and the galaxies behaved correctly on paper. The explanation could not be discarded. The substance could not be found. That made the situation increasingly uncomfortable. The evidence from the galaxies remained strong enough to trust. The proposed solution remained successful enough to use. But success inside calculations was no longer producing success in direct detection. The old confidence began to erode. Not because the observations had failed, because they had survived. The motions of the galaxies now seemed more secure than the explanation built to account for them. The measurements were still standing. The missing substance was not. And if modern astronomy continued relying on this unseen component, an unsettling question was beginning to grow. How much of the current picture depends on something that has never been directly found? The consequence did not stay inside a handful of distant galaxies. It spread into the way the universe itself is described. The same invisible component became woven into the larger picture of the universe itself. Models of cosmic structure, galaxy formation, and large-scale behavior all continued relying on mass that could not be directly observed. The pattern repeated again and again. Visible matter alone was not enough. Additional mass had to be included for the observed behavior to make sense. That changed the nature of the problem. What began as an unexpected motion in the outer regions of galaxies gradually became a foundational assumption built into modern cosmology. The invisible mass was no longer acting as a local fix. It had become part of the framework. And that creates a remarkable situation. Some of the most important features of the universe are not mapped from direct observation alone. They are inferred from consequences, from motions, from gravitational effects, from behavior that appears to require something more than what telescopes can see. The original contradiction never truly disappeared. It expanded. A measurement problem became a dependency. The observations can be seen. The mass cannot. One is directly observed. The other is inferred. Yet modern cosmology still depends on both.